Alright, some of the next characteristics mentioned for fiber is attenuation and bandwidth. Well, let's take a look at attenuation real quick. Remember, with copper, we have resistance and those sorts of things to weaken our signal over distance. That's why copper was always set as 100 meters max. Well, fiber works a little differently. As I change my light source, the wavelength of my light source, and change the diameter of my fiber, multi-mode versus single mode, all that factors together. So if I look at a typical piece of 62.5 125 micron multi-mode fiber, I get about 3.5 decibels per kilometer loss at my 850 nanometer light source. That's your typical LED, you know, basic light source that I would use. Well, that drops to about 1/3 of that, 1 decibel per kilometer, when I change my wavelength up to the 1300 nanometer light source. Now, again, when we get to the fiber chart, we'll talk about this a little bit more, but this is a more costly light source. Again, like upgrading part of my car, a performance part that's going to cost more money, but I get better performance. I have less signal loss. I have less decibel loss. If I move up to a single mode fiber, again a smaller core laser light source, and I start using a 1310 nanometer wavelength light source, again more expensive. Single mode fiber is more expensive. 1310 nanometer light source is more expensive. I'm getting about a half a decibel per kilometer loss. And I jump up to the 1550 nanometer light source, again more expensive. I'm down to about 4/10 of a decibel per kilometer loss. But again, if I'm looking at long haul single mode connections, I'm probably looking at this stuff down here. But as I see on this, I get less attenuation, less signal loss, less attenuation with single mode fiber. That's why single mode fiber is usually relegated for WAN use, and your multi mode fiber is acceptable at a couple hundred meters for LAN use. And here's just some graphs I pulled out to show you as I go from a multi-mode fiber to single mode fiber. You can see your attenuation drop pretty significantly. And as that wavelength increases, the attenuation is dropping too. You're seeing that as we go from multi-mode to single mode, and as I'm increasing my wavelength, I'm seeing my attenuation drop. So the bottom line here is as the wavelength is increasing, more expensive light source, but as the wavelength is increasing, attenuation is decreasing. So in other words, longer wavelengths equal more distance. That's a handy little tidbit to keep in the back of your brain when you're dealing with fibers. My bandwidth of fiber, this is something people like to kind of say, well, what's the bandwidth of fiber? Well, it's actually a product. It's a bandwidth and distance product. For 500 megahertz per kilometer fiber, which again, as you buy fiber, there's a rating on it. If I have 500 megahertz per kilometer fiber, my usable bandwidth of 500 megahertz at 1 kilometer. As I drop to, usable bandwidth at 1 kilometer length is 500 megahertz. So I'll get it yet. As I drop my cable distance to 500 meters, I get 1,000 megahertz of bandwidth. As it drops to 250, it's increasing to 2,000 megahertz. So the shorter the distance, the more bandwidth I'm getting is what it amounts to. So you can't nail down with fiber optic, well, am I getting? It has to actually do a bandwidth and distance product. One of the next things they mention is connector types. Again, we're going to spend more time on this in Chapter 11, but I want to at least introduce you to the different connector types you would encounter. ST, SC, MTRJ, and LC. These are actually the kind of the common ones through time that you keep running into. The ST was very common in earlier fiber connections. It's almost like a little twist lock, almost like a mini BNC connection to twist locked on. That got replaced by SC. This got used very commonly. It's kind of like a square friction push, I should say push friction fit. You slid that into your switch port or media converter port, just kind of friction fit in there. This got replaced by MTRJ for a little bit, not long, but for a little bit. This was a little, kind of reminds you of like a mini RJ45. That's the MTRJ. That's kind of the connection there. This, both fibers are in one connector. If you look at the other ones, they are individual fibers per connector, take up a lot more space. This was supposed to be a low profile, both fibers into one connector, but it's hard to get both of those aligned. The modern connection that you run into for probably most things today is going to be LC. And these are two these two connectors take up about the same space as one of these back here. So smaller form, but you notice there's two fibers right there. That's kind of the one. This is the one that you see most of the time in switch ports or small form pluggable modules that you'll be plugging in your switch. The outer insulation I have on fiber, well, this is going to sound like a repeat. I have three different types: general, riser, and plenum rated. General purpose fiber optic patch cable that I would use between devices inside of a closet might be general purpose polyvinyl chloride insulation on it, flexible use for patch cables, and the code on the outside of the jack would be OFNG or OFCG. Optical fiber non-conductive general, optical fiber conductive general. They do have conductive insulations for some purposes, some applications. You want to send remote power to some device. So if I look at this for our purposes, if I look at OFNG, G is telling me general purpose. As I look right here, OFNG, OFCG, general purpose, that would be a patch cable inside of a closet. I do also run into riser rated fiber optic cable, just like before, OFNR, OFCR. R is telling me riser rated. This piece of fiber could be used between closets to connect switches in closet on the first floor to closet on the second floor, closet on the first floor up to closet on the third floor kind of thing. And last one is your plenum rated cable. Just as before, plenum rated spaces, etc., etc. My cable jacket label is going to be something like OFNP or OFCP, and P is telling me plenum rated. This could actually be installed in plenum spaces in my building. Other things you run into with fiber optic is a color coding. Typically, if you look at the insulation on the fiber, things that are fiber optic that's orange is typically multi-mode fiber. Fiber that is aqua colored, bluish color, is typically laser optimized 10 gig multi-mode, and yellow fiber is typically single mode fiber. That's just kind of a general rule of thumb. Again, you would want to look at the marking on the side of the cable, just like we did with twisted pair. I will see something about manufacturer, part number, rating, typically fiber size. This is where you pay attention to those numbers we talked about earlier. And then a plenum rating. I would typically find those things on the side of the fiber. When I'm installing fiber, fiber is typically installed in something called interduct. That's what this orange tube here is. This kind of reminds you of something about the size of like swimming pool hose, like a large garden hose. This is actually installed up in your ceilings or your racks, and then you carefully pull the fiber through it. So it's acting as a low friction path for fiber installs, and also a form of protection for the fiber once it's in place. So when you buy this stuff, it typically comes with a rope already installed, a pull rope installed, and you carefully tie the fiber onto it. They make special little, doodads to clip on the end. They call them pull eyes that I can attach onto the fiber, and I carefully pull it through the inner duct and install it in there, and then plug it in my devices and so forth. So that's typically how I'm going to install my fiber, with a piece of inner duct. There is special types of fiber that you run into as I start dealing with fiber that's outside. Either between telephone poles or under the ground, I run into either aerial or underground fiber. Aerial, this would be the stuff going between telephone poles that somebody like a Comcast or Verizon is installing. This actually includes, along with it, typically a cable. This is attached to the pole to support the fibers underneath, because otherwise, if you try to hang it with the fibers would break. They're too delicate. So you anchor the steel cable to the poles, and the fiber kind of goes along for the ride. That'd be an aerial type of fiber optic. Otherwise, if you're going to bury it underground, you would have an underground rated or armored, if you will. And the armoring on there is to resist, as the ground freezes and thaws, it starts shifting and moving around. If I have an ordinary plain old piece of fiber in there, as it's moving around, freezing and thawing, it's going to snap the fiber. I have a fun story about that. Ask me that sometime when you see me, about a indoor rated fiber installed outdoor under the ground, and it snapped during the first freeze. Typically, I'm also going to find this underground armored cable, if you will, filled with something called Icky Pick. It's a gel that goes in there that kind of reminds you of like a toothpaste. The gel that goes in there is there to try to protect the fiber for any kind of moisture. So if you did get a little break in the insulation, it's there to try to keep the moisture out. But it's also there for another reason, hence the name Icky. Um, it does not taste well to critters. So as critters try to chew through the cable, chew through the fiber, they get to this gel and go, yuck, icky. And they don't want to chew through the cable. That sounds bizarre, but critters want to do this. So typically in this underground rated cable, I also have Icky Pick in there. It's like a little, kind of reminds you of like a gel toothpaste, if you will. So here's a piece of armored cable. The armoring is not there to stop a backhoe, but it's there to keep from critters chewing through and the ground freezing and thawing and heaving, trying to keep from breaking the fiber in there. So I do run into a couple special applications for fiber optic, the aerial and the shielded. You also run into when you're outdoor, sometimes the fiber or the insulation needs to be UV rated because it's going to be in the sun. Temperature, UV rating, that sort of thing. So you sometimes run into special insulation on that for that purpose. One of the last thoughts I want to mention in this chapter is, since we're talking media, you sometimes run into the need to convert your media from one type to another. If I have a copper connection on my switch and I need to run a fiber cable, I could take the copper patch cable from my switch, plug it into a media converter, and the media converter is converting it over to a light signal, and I can plug my fiber patch in here and go, the 500 meters to my other closet. A media converter is just doing that. It's converting the signaling from one type of media to another one. So I plug in a copper patch cable here, electrical signals. It's reading the electrical signals, then spitting out over here light pulses that I can plug into my fiber optic. Well, this is an older style media converter. You still see them, but it's an older style. Newer style media converter comes in this form, small form pluggable, SFP, small form pluggable. This module slides into a switch port. This guy right here, that's an empty SFP port. That's an RJ45. There's an SFP that looks similar but not the same. Okay, there's your SFP port. That SFP module slides in there, and that allows me to plug my LC fiber cables right into the switch. So again, if I'm connecting closets together, I can plug my patch cables right into that. All right, there is all of our doodads and tidbits about media. Hopefully that'll kind of sort out some details for you.